Welcome back to another lecture, and today we are going to see an overview of the electromagnetism and a brief historical introduction. Now, very similar to the Newton's laws, the Coulomb's law is also based on some experimental observations. The force between the two charges, we will say that F is the force between the two charges. The force will increase if Q1 increases. Not only that, the force will increase if Q2 increases, and because of the product is there, any one of them increases means the force acting between the two charges will increase. The increase is what is written in the numerator. And when you are coming to the dependence with respect to the decrease, you write it in the denominator. And the quantity that is responsible for the decrease is the distance between them, and in particular it varies like 1 over r square. By doing some experiments on the measurement of force, what is done by Coulomb is this is measured. So these two things are measured, but Q1 and Q2 we don't have, or he could not measure what is the value for the Q. There is the only information that he has is there is some amount of charge Q, that's all about it. And he has an idea about how to increase the charge or decrease the charge. Not by exact value, but a rough way. The rough way of increasing or decreasing is like this. You know that charges were known to be created because of the friction. That means rubbing two materials against each other. For example, if you take a transparent plastic rod, a plastic rod is there, but that is a transparent one. That is called perspex. Such a material you take, transparent plastic rod, and then you take a woolen cloth and then rub it. When you're rubbing, you make a rough calculation that suppose if you are going to make a rubbing by 10 times, for example, then you say that that is Q1. But you do not know what is the value. That is the interesting point. You don't have the value. But however, you know that there is some charge which is present in the system. And that you denote by Q1. Now Q2, what you have to do is, if you want to increase the number of charges, what Coulomb has done is that instead of rubbing it 10 times, now you rub it for 20 times. And therefore, in this process, he has made an assumption that 20 times rubbing is going to give you more number of charge in the system than the previous one. So in this way, Q1, Q2 has been increased. And then he calculated that 20 times rubbing means he got more number of forces coming. 10 times rubbing means less amount of force is coming between the two charges. And of course, the force is measured by a technique called torsion balance or the torsion pendulum. Basic principle is based on the torsion pendulum. So that was the technique used for the force measurement. And distance is, of course, you can easily measure. So the idea is that without knowing the exact values for Q1 and Q2, he has come to this kind of an expression which works very well. If you repeat it for several times, this particular law appears to be valid, and therefore he has put forward this result in 1785. So Coulomb is not the person who gave the frictional electricity. So that point also I will mention here, because we are writing this year, say 1785 I have written here, and then 1685 for the Newton's law. So since I am talking about the friction between the two materials that generated the electric charges, you should remember that that is not the one which is put forward by the Coulomb. That information is known much earlier. So roughly about 2500 years, during that period itself, people are aware that the friction between the two materials, especially the insulating materials, they generate some kind of spark or some kind of a small shock, some kind of things will come, and therefore from that they got an idea about the electricity. And people have already given a name here. So let me write down the name here. The Greek name has been given, and note that there is a K here, not for the electron that we know, or not for the electron that we are talking about in today's scenario. In today's scenario, electron is different. 2500 years back, the name electron is something different. It's totally different. It is an ember. So basically, it is a kind of rock, whatever it is. If you are not clear about the word fossil, you simply understand that it is a kind of a rock. It's a transparent rock. And how the rock has formed is resin. Resin is something like a fluid that comes out from a tree when you cut the tree. So that particular resin is very thick fluid, and then this thick fluid, if it is allowed to leave it without disturbance for about say 10 million years. No, time is very important. 10 million years. During that kind of period, the resin get transformed to rock, very strong rock-like material, and it is a transparent, and it is very strong. So that's why we use the word rock. So people got interested in seeing the color. Of course, it's very it is the color is interestingly orange color, and it is very transparent. So people got attracted towards this kind of stone. That is how the people came to know about this amber. And because the rubbing of amber with another material like fur or woolen material, for example, then you get the static electricity. And this name electron was given by the Greeks with a K here. So the meaning is that the electron at that time is basically a name given to the rock, not the electron that we are talking about today. So today what all we have done is we have taken this particular word and then given the same word to the electron that we are discussing in today's scenario. So that is what I want to explain to you. And the more important point here is that Q1, Q2 values are not known. That is very important. You forget about, there is some story here, that's fine. But the important point to be noted here is that in this equation, so let me write down that in this particular equation, this is a scalar. So everything is a scalar here. Direction, that was not very important. But since there are only two charges are present, automatically a straight line will come into picture, and that is the direction in which it acts. So the first point is that they have used the scalars for the calculation, first point. And the second point is that the values of the Q1, Q2 are unknown. So let me write down that. Okay. So that means magnitude, that means numerical values, they are not aware of this. Now let us see what happened after 1785. You go forward by something like 100 years or roughly 100 years. In the year 1865, Maxwell has put forward. So this is the very important contribution that has led to the great development to the field of electromagnetic theory. So whatever electromagnetic theory or whatever electromagnetism that we are talking about in today's scenario is the mathematical theory developed by Maxwell, and that is in the year 1865. So you can see that there is considerable time difference between the establishment of the Coulomb's law in 1785 and then to 1865. Of course, Maxwell has not done any experiment. His main work is to understand whatever experimental laws that have been given in the historically, the laws such as Coulomb's law or the Faraday's law or the Biot-Savart law. Any law that you are going to consider, all of these things came much before 1865. And the names that I told you, that is the Faraday's law or the Biot-Savart law, none of them are based on some computation, or none of them is based on some theoretical foundation. All of these things are some experimental observations. So you have a collection of experimental observation, namely the Coulomb's law, Biot-Savart law, Faraday's law. So keeping these experimental observations, Maxwell want to understand these experimental observations in a mathematical way. So Maxwell's contribution is mainly to consider these expression in terms of vector calculus. Why vector calculus is used is because of the reason that people know that this force should be a vector quantity. So here I am putting around here. This force should be a vector quantity. And therefore, why should we write this equation in the scalar form? So let us first of all write down this in the vector form. That is an idea. Similarly, when the electric field is calculated, electric field is a vector quantity. Biot-Savart law, when he gave the magnetic field, once again, the original expression was in the scalar form. So Maxwell has considered and converted everything in the form of a vector. Once you have a set of equations in vectors, he further demanded that once you have these vectors, they should also satisfy the mathematical identities. So you can't have a vector and then not satisfying the vector calculus rule. That is not possible. You understand what I mean to say? So this is little bit you have to think. What I'm trying to say is, see, if you have, let us say that if you have two numbers, 7 plus 2, I have two numbers like this. And then I have a mathematical formula. I have a formula like this, a plus b whole square. Some formula is like this. And then you know the expression. Now, what I am trying to say is, there is a mathematical formula like this. I have two scalars like this, 7 and 2. 7 and 2 are two numbers. What Maxwell is trying to explain to us is that whenever you have two numbers and whenever you have a formula like this, these numbers should satisfy this automatically. It has to satisfy. That is what the demand. If it is not satisfying, then there is something wrong. That is what is the argument of Maxwell. That means if I am going to do a calculation like this, 7 plus 2 whole square, I don't know what answer will come. But without doing my calculation, I expect that the answer should be equal to 7 square plus 2 square plus 2 into 7 into 2. Is it coming or not? That you have to verify. If it is not coming, then there is something wrong with that or some trouble is there. If it is coming, then you will be happy. This is what is the idea of the Maxwell. Maxwell have two things. On the left hand side, Maxwell had the experimental observations given by Coulomb, Biot-Savart and Faraday. All of them are experimental evidences. That he is having on the left side. On the right side, Maxwell is having equations of vector calculus. What Maxwell is trying to say is that on the left hand side, the quantities, the physical quantities are vectors. If it is so, they have to obey the rules of vector calculus. Are they obeying or not? That's the question. So that is the work done by the Maxwell, and he has ended up in saying that the experimental observations are obeyed well according to the rules of vector calculus. So now you understand how important vector calculus is for the case of electromagnetic theory. It's very fundamentally, it's very important. It's very crucial. Therefore, vector calculus is very, very important if you want to do any calculation in the case of electrodynamics. So that is the idea. So idea is now clear, right? So what is the starting point of the Maxwell's in the understanding of the electromagnetism? So in this way means once Maxwell has put forward his mathematical theory, then we say that the electromagnetic theory is understood. That is what people say. Now EM means electromagnetic, then theory. So electromagnetic theory is understood in the sense that when you go back in time and when you say that only Coulomb has published his result, people did not understand further details about that. So that is the meaning of understood. Understood means people know how the electricity is connected to the magnetism, how magnetism is again connected back to the electricity, and how electricity and magnetism are connected to the optics. No, that kind of knowledge came into existence only after the Maxwell's discovery. Before that, people do not have any idea why there should be any connection, why at all there should be any connection between electricity and magnetism, and why electric and magnetic phenomena should affect optics. So for such questions, there were no answer before the Maxwell's discovery. So remember that the mathematical foundation of the electromagnetic theory is based on the vector calculus. And the vector calculus will be done on a particular geometry. Of course, geometry has to enter into picture. Vector calculus can be done on Cartesian system. Vector calculus can be implemented on any coordinate system. That's why we have already started with the cylindrical system. And then later we will see the spherical polar coordinate system. So the overall idea is now clear that starting with the case of the Coulomb's expression that you have here, it gave you some idea about the electricity, only some idea, but clarity is not there. So only after the Maxwell's explanation based on vector calculus, people understood electromagnetic phenomena in a much better way, and in a way that we are working with. Okay, anything that you know with, say, antenna, how the electrical communication takes place, how the optical fiber optical cables work, everything is based on the Maxwell's formulation. Otherwise, people do not know the propagation of electromagnetic waves. Hertz has discovered the propagation of electromagnetic wave experimentally, and Maxwell has verified that his equations are in agreement with the Hertz discovery of electromagnetic wave propagation. So that was a very big discovery, and of course they got the Nobel Prize for his discovery of the mathematical foundation. Okay, he has not done any experiment, but the important point is that everything is understood using mathematics. And that is exactly what we are going to do in the first course on electromagnetism. Namely, that you take the original experimental equation that is like this: F is proportional to Q1 Q2 by R square, and then understand everything in terms of a coordinate system, and then write the expression in the vector form. And once you have the vector form, there will be some vector identities in mathematics, and you have to see whether how they go side by side. That is the overall idea. So that is why I have written overview. Overview means uh, overall, how do you visualize electricity and magnetism phenomena? Okay, electricity and magnetism doesn't stay independent of each other. They always go together. So the question comes, why it should go together? So the answer is there in vector calculus. And the meaning of electricity in today's scenario is very different from the meaning of electricity at the time of Coulomb. What way it is different is, the meaning implied by this word is only static electricity. Okay, static means something that doesn't move. If you have a charge, that charge will be staying at the same point without any movement. And that is the meaning. That's called static electricity. It's also known as frictional electricity because due to the friction, those charges came into existence. In terms of today's scenario, this particular terminology has been renamed. Okay, that is why people have changed the name, and the correct name that can be used to describe the scenario where the charges are stationary is electrostatics. When electrons are moving, you can always say electrodynamics. So J.J. Thomson discovered the electron, that you know. But interestingly, there is one more interesting point. He discovered the electron, fine, he got the Nobel Prize, that's fine. So even though electron is discovered, its charge is unknown. So that somebody has to measure. So later, that is roughly about say 10 years later, Millikan has performed an experiment which you may be knowing, what is known as the Millikan's oil drop experiment. This experiment has given some idea about the calculation of E divided by M. That means electric charge divided by the mass of electron. But even after calculation of the E divided by M of the electron, what is still remains unknown is the charge of the electron is unknown. So people were trying how to find the value of the E, that is the charge of the electron. Now why people are so much interested is, again let me go back in the first place. In the Coulomb's law, you have written Q1 here. So you see the green color cursor. So there is a Q1 here. So without knowing what is the value, how we can proceed further in the calculation? So that is where the problem is. People have been searching what are the values for this Q1 and Q2, how to find them. So in order to find them, you need the value of E. Okay, E means the electronic charge. So even after discovery of the electron, the value of the charge value is not known to you. And interestingly, you see that again you go back little bit, and even though Maxwell's mathematical formulation, everything has been done so fantastically, and then electromagnetic wave propagation has been tested in a very successful way by Hertz, and he himself got the Nobel Prize. Even after so much achievement, the value of the charge of the electron is unknown. Okay, so that happened much later. You can see that this is an 1865 Maxwell's work, and then you see that the discovery of the electron, and followed by 1907, and followed by 1913. So 1913 is the time where the electronic charge, that means value of, and of course by Millikan. So because Millikan was the one who was doing the oil drop experiment, so he continued the experiment further and further, because he already found E by M. So somehow you have to manage to get the value of E from E by M. Okay. Interestingly, we don't know what is the mass of the electron. If you know the mass of the electron, you multiply, you get. But we don't know that also. That is why the struggle was there, and therefore Millikan himself later found out. This is first discovery. The additional discovery is that, and not only that, there is an and here, and any charge that you are going to get will be a multiple of 1.6 into 10 to the minus 19. Plus minus will change depending on the charge, but the number is very important. fractional multiples are not possible. That is the conclusion in 1913. So this is very important, one of the very important conclusion that led to the modern physics. So we will not deviate our topic and go to modern physics. But remember, therefore, this is one of the very important experiments in the history of science that changed the concept of the classical nature to the quantum nature. Okay, the quantum nature is what we call the modern physics. Okay, so this is the one of the experiments that gave evidence that the discreteness of the charge is present in a natural way. So this is called the discreteness. Discreteness means you can have one electronic charge like this, then you can have two of them together, or you can have three of them, or you can have four of them. But if you draw a line like this is a continuous charge distribution. So this is continuous. In the continuous line, you cannot say how many dots are there. Here you cannot say. You can, if you want to really say, you can tell in terms of some fractional value. But here you can't say how many dots are there here. You cannot say any fractional value. You have to say compulsorily an integer number. Okay, you have to say 6 of them are there, 7 of them are there, 8 of them are there. You can't say 500 dots are there. Such option is not there. But here such option is possible. And therefore what happens is this continuous charge distribution is rejected. So this is gone. So this is accepted. So this is known as the discrete. This conclusion is, remember, is based on experiment done by Millikan's oil drop. But this discrete nature of charges is not required in order to verify the Coulomb's law. So Coulomb's law doesn't demand such kind of discrete nature. It only tells that if two charges Q1, Q2 are there, they get multiplied, and if Q1 increases, force increases, and that's all about it. But the discovery gave additional information, and therefore the development of new subject, namely the modern physics and quantum mechanics, started after Millikan has given this kind of discrete nature of electron. That means you see how the science is growing. So they started to work with one thing, and they started to got additional information, and the additional information provided a pathway for the development of new subject, and the new subject grows like that. So the overall idea is now clear that even without knowing the charge value itself, Coulomb gave the Coulomb's law and in the scalar form. And we will see now how Maxwell has rewritten them in the vector form. We are not going to do the detailed derivation because the complete derivation of the equations as done by Maxwell, that we will be doing in the second course on electromagnetism. So anyway, that we will see in the next class.